Yeah, until now, the problems what we have looked at for the deflections of beams, they were mostly statically determinate structures. And since they were statically determinate, it was easy for you to find the reactions and express the moment in terms of that reaction, and then plug into that equation ei d square y by dx square equals to moment of x. And then the only things you needed to compute were the constants of integration. Now, in this lecture, what we are going to look at is how do we deal with statically indeterminate problems where you do not know the reactions. We do not know all the reactions that are there in statically indeterminate problems simply from the equations of equilibrium. So we will see that how this is also one of the first places in your curriculum of structural engineering or civil engineering. You will see that how we can use some of the concepts of the deflection of beams to find the unknown reactions in statically indeterminate structures, and from that how can we find the deflection of statically indeterminate beams. So if we go ahead and take a look, so for example, you have statically indeterminate beams, maybe something like this over here, right? So here we have a fixed end at one end, it's a cantilever, so it's a propped cantilever. You have a cantilever and a simply supported end at the other. Now from here you can tell that this beam is statically indeterminate to degree 1. Why? Because you have a reaction here, a fixed end moment here, and you have a reaction here. So you have three unknowns, but your only saving grace are two equations of equilibrium. The one along the x direction doesn't matter, so you're only left with f of y equals to 0 and the the moment about a point equals to 0. So you have three unknowns, so you will not be able to solve for all the reactions using just the equations of equilibrium that is there, right? So these are the reaction components that is there. So you have this vertical reaction, this is vertical reaction, this is the moment. Also you have it says that four unknown reactions. You have the horizontal reaction, but that is 0 in this case, because you have no other forces in the x direction. So eventually you have three unknown reactions that you have, but two equations of equilibrium, right? But if you take a look at this beam and then if you apply, say, the general equation, see this equation what we have, it comes from the general equation itself for the moment. For example, the precursor to this equation is nothing but what we had seen earlier, that my ei d square y by dx square equals to m of x. If we take this one and if we integrate it two times, this is what we had seen before, you end up with two constants of integration. So you might be thinking that you're actually making your life worse because you already have one unknown reaction. Now on top of that you're introducing two constants of integration, but actually it is not. You're actually making your life easier because these three additional equations, these three provides additional equations for the boundary conditions. And how does it do that? See, at this particular point we know that the deflection is 0, right? So that is one condition it gives you, that is y equals to 0 at x equals to 0, y equals to 0 at x equals to l. In addition to that, there is one more condition. Can you think about it? Yes. So here you see at this cantilever end, since it's cantilever over here the slope also must be 0. So ei dy dx must also be equals to 0. So although you are introducing your two more unknowns, you are providing three additional equations to take a look at that. And this picture essentially shows you that at x equals to 0, theta, that is the dy dx. So theta is nothing but your dy dx over here, that is 0, y equals to 0, and x equals to l, y equals to 0. So let's go ahead and take a look at a problem for the statically indeterminate beams. And also you must keep one thing in mind, that this method also that you are learning, that this only works when you have a continuous kind of, if your moment is a one single function along the length of the beam you are looking at. If you have discontinuities, the load and all, you will end up in problems with then, because in that case you have to have the continuity conditions of the deflections and so on. So first let's take a look at a simple example problem of a propped cantilever beam with a triangular loading. The example problem that you see, you have a propped cantilever beam with a triangular loading over here. What it asks you is to find the reaction at A, derive the equation of the elastic curve, and find the slopes. It also asks you the slope at A over here. Okay. Now if you take a look at this beam, you will have, since all the loads are in the vertical y direction, you will essentially have three reactions over here. You will have a vertical reaction RA. Here you will have a vertical reaction RB, and since it's a cantilever end, you will have a moment mb. There are three unknowns. Your equations of equilibrium, two equations of equilibrium are not going to help you. So here we will see that how our concepts of beam deflection helps us to solve this particular problem. Now at any, for this beam also, if I draw a section at say any distance x over here, and if I write the expression for the moment at that one, so let's just go ahead and draw the free body diagram of this small chunk which we can separate out, and draw the free body diagram and find the moment, because eventually remember we have to go back and substitute to ei t square y by dx square equals to m of x. So if first I will draw the free body diagram of this one and write the expression for the moment. Now this triangular load can be replaced by an equivalent load which is acting at a distance of 2x by 3 from here, or x by 3 from here. Now once we have marked this, if you write out the equilibrium equation, you will get an expression for the moment as, this is the expression for the moment that we got over here. And now we are going to use this expression for the moment and substitute in our equation to get the deflection. So this is the expression we get. The first one is for the slope, and this is after you integrate it one more time over here. So now you see this equation has three unknowns. Your RA is an unknown over here, and your C1 is an unknown, and your C2 is an unknown over here. But now with this one, you have now introduced three boundary conditions. Why? Because at this left end over here, at x equals to 0, my deflection equals to 0. At x equals to L, my deflection equals to 0, as well as at x equals to L, my slope, that is dy dx equals to 0. So let's go ahead and write the boundary conditions. So you have introduced three boundary conditions over here. You have three unknowns in this one over here. So you can, mix and match and play around with it and find out the values of the RA, C1 and C2. So I will go ahead and write the values that we get over here. Remember, you have to use both these equations over here because you have an expression for the slope. So you can go ahead and try that out. I'm going to write the final expressions for RA and C1 and C2. So this is, you see, using now our deflection criteria that we have over here. Now without using any equation of equilibrium alone, I have found out what is the value of RA simply using the deflection steps. Now if you want to find the other reactions, the problem does not ask you that. It is now very easy to do. You can use your regular equations of equilibrium, that is a vertical load equals to 0 and moment about any of the points if you take as 0. Since RA is already known, you can easily find MB and RB. We are not going to do that here since the problem does not ask that. However, the problem asks you to write the equation of the elastic curve. So for this equation of the elastic curve, I already know RA, I know C1 and C2 over here, and it also asks us to find the slope at A. So this one over here, after substituting RA and C1, we will get the slope at A by putting x equals to 0. So let me go ahead and do that. You can come back and check. So this is the slope and this is the equation of the elastic curve. So how do we represent the slope over here? See, you have over here, sorry, this is a negative slope. I missed the negative sign. So it is a negative slope that you get over here. So that means your beam, and you, as you can see from the figure also, the beam sort of deflects like this. So let's just draw the deflected shape of the beam. So here at this point you see the slope must be equals to 0 over here because there's a cantilever end, and at this particular point your slope is this one, minus W naught L cube by 120 EI. So I hope this problem example was clear to you, that how we used our concepts for deflection of beams to find the unknown reaction and as well as the deflection or the slope at different points of interest in the beam. Now again, just to remind you, this was possible to do in our case, and possible and easy to do because you had one continuous equation for the moment that is valid across the length of the beam. Now if you have intermediate disturbances like a point load or a point moment and so on, then it becomes complex. You have to use some continuity conditions and so on.